Hello everyone, welcome to my channel. So today we will learn about the common base configuration of NPN transistor. So there are basically three regions or three terminals, you can say. It has emitter, it has base, and it has collector. And the base region is made very small. You can see that the thickness of the layer which is sandwiched between these two regions is very less. Now what about the biasing? So we have two junctions. So first junction is known as this junction is known as emitter base junction. So this junction is forward biased. You can see that the P is connected to the positive end of the supply and N is connected to the negative end of the supply. And this junction, this is known as the collector base junction. So the collector base junction is always reverse biased. So if you connect N terminal with positive supply and P with negative, you have a reverse biased junction or reverse biased condition. Now what about the symbol? If we move on for common base, then the base is kept common between input and output side of the configuration. So this is our actually input port, input side, and this is our output side. So let's say we have currents. So it is made like that this current should be equal to base current plus collector current. So IE is equal to IB plus IC, where emitter current is the input current and collector current is the output current. What we want the input characteristic for this NPN common base transistor. So what is input characteristic curve? It is a curve which is plotted between input current, which is IE, and input voltage, which is VBE or VEB, for a fixed collector to base voltage. So it is defined like that. It is input driving characteristic, or you can say the input characteristic curve for NPN transistor or any transistor. For this now I am using an NPN transistor, and you can see that the curves resemble diode characteristic. Why? Because the emitter current is actually equal to IE naught exponential of VBE upon eta VT minus 1, which we already know it is a diode current. Okay, and we know that it has a cut-in voltage. The diode current will rise exponentially after we reach a certain cut-in voltage. So the VBE value for the diode is closely resemble to 0.7 or 0.6. You can see that. So in this plot, what you are getting, you are actually getting two information. So first information is that as you increase VBE, IE rises exponentially, as given by the equation, which is IE is equal to IE naught exponential VBE upon eta VT minus 1. And for higher VCB, as you increase VCB, the curve will shift. You can see the shift. For 1 volt it is here, and for 10 volt it is slightly shifted, and for 20 volt it is shifted more slightly towards the left side. Why? Because of the Ali effect. Ali effect we will discuss later. Okay. Now the second information which we want to get is our output characteristic curve, which is plotted between collector current, which is our output current, and VCB. And VCB is actually collector to base voltage, and it is also output voltage. So for a given output current and output voltage, we give various values of IE. And what is a transistor action? Transistor action is that the IC should be equal to IE. You know this formula, IC should be equal to alpha IE. Okay, and for ideal transistor this alpha should be 1. So the IC should be equal to IE. If what we inject at the emitter collected at the collector, then it is a proper ideal transistor. Okay, so the input current should be equal to output current. Let's say what are the regions. So for this different color emitter current, we have three different regions. So first region is cutoff region. Cutoff region is when you give emitter current 0. So emitter current 0, which ideally means IC should be equal to 0. But IC is not 0. In practical situations, IC is not 0 because there is a reverse saturation current. You know that in diode as well, there is a reverse leakage current flowing through reverse biased junction. So BCB is reverse biased, and because of this voltage which is reverse biased, you have IC not equal to 0, but it is equal to ICBO, that is collector to base current with emitter open. Emitter open means open circuit means what? IE 0. So when IE 0, we have a notation ICBO, that is collector to base current with emitter open. Now what happens when you get active region? So active region is this. So when you get IE 1 milliampere, you get IC also equal to 1 milliampere. Okay. IE 2 milliampere, you get IC 2 milliampere, IE 3 milliampere, it is also 3 milliampere. So you get transistor action here. That is why it is known as active region. Active regions means transistor will act as an amplifier. What kind of amplifier? Current amplifier. Okay. It is a current control device. It is not a voltage control device. So whatever input current you are given, you are getting the same, almost same output current. Okay, that is our transistor action. So the curves are flat, but after certain VCB you get higher currents, which is a effect we will discuss later. Now what about saturation region? So in saturation region we have collector based junction forward biased. You can see in the graph when the voltage of VCB is slightly shift toward the negative side, that is when you make this junction instead of reverse biased forward biased, then what happens, collector will not collect all the carriers. Whatever injected carriers you are passing, it will not collect all the carriers, so collector current will start to drop. That is our region of operation. So in saturation region of operation, it will lose its amplification property. So that is all about we know about common base configuration. If you like my video, please like, share and subscribe my channel. Thank you.